Today we are going to discuss backpropagation, as we mentioned at the end of the last class. So it's going to be a very interesting class with a lot of examples to illustrate this concept. But before we start, I would like to acknowledge with respect the Lakwangan peoples on whose traditional territory the university stands, and the Songhees, Esquimalt, and Wasanich peoples whose historical relationships with the land continue to this day. Today's lecture is going to have the following structure. We'll start by doing a bit of a recap on neural networks, just so we are fresh on the latest concepts. Then we are going to talk about the computation of gradients for more complex networks. So a little bit of an introduction, and then the idea of using computational graphs to help us in these calculations. And then we are going to get into backpropagation. And the best way to really understand how backpropagation works is to look at a lot of examples. We'll start with two simple examples that are just using scalars as inputs. So the parameters that we are going to calculate the loss with respect to, and then start changing the values, are all scalars. Then they're going to become vectors, and then finally matrices. So a very quick recap on what we discussed last Thursday about neural networks. Neural networks are combinations of weighted sums and activation functions. They learn distributed representations of the data, as we said. So for traditional linear models, each row of your weight matrix would represent a template. You can think of these classifiers as doing then a lot of template matchings at a time. And then the result of each template matching would give you the score for a particular class. For neural networks, we know that this is not the case. So if we are working with a two-layer neural network, for example, we know that we have a single hidden layer, and the number of dimensions of this hidden layer is going to tell you how many smaller templates you're going to have. In the examples that we are using, our hidden layer had 100 hidden units, if I'm not mistaken. So we have 100 small templates in this first weight matrix. Now we have actually two weight matrices, right? So the first weight matrix is going to tell you what these little templates look like. They are not always going to be interpretable by a human being. And then the first hidden layer is going to tell you, okay, for this particular input, how were these smaller templates activated? And then based on these activations, they are going to be recombined again in the second weight matrix for the final output. This is, of course, the representation of a two-layer neural network. We can have a neural network with any given size. Because of the activation functions, we discussed a lot about activation functions, right? We discussed the fact that activation functions are responsible for providing these non-linear capabilities to neural networks. So because of them, neural networks can represent non-linearly separable data in feature spaces where they are linearly separable, and then perform classification on them. So we showed examples of data that was not linearly separable after the application of an activation function in a new feature space they were. So this is what neural networks are doing. In the input space, the decision boundaries that they create after this transformation are nonlinear. So they look like this, for example, for a certain number of hidden units. We then discussed towards the end of the class about this idea that we can create functions that we call bump functions using just 4 activation functions, in particular ReLU. So putting 4 ReLUs together, they are weighted and shifted differently, but putting them together, we can create these bump functions. And then composing a lot of these bump functions together, we can approximate any continuous signal, given a couple of caveats. For example, that it is continuous. So this is the idea behind the universal approximation theorem. We ended the class discussing the fact that the landscape that they create in terms of the loss, so the objective landscape is not necessarily going to be optimizable using the algorithms that we were talking about, because sometimes we are dealing with these kinds of scenarios, so they are definitely not convex, right? So if we are using our algorithms like the stochastic gradient descent with momentum, how can you go to a higher loss in a particular space and then go down and then go up again? So they are extremely almost adversarial to what we are trying to do. But as I said as well, it turns out and lucky us that this is the case, that the optimization algorithms that are theoretically guaranteed to solve problems that are convex also turn out to work well with these kinds of scenarios. So otherwise, that would be super problematic for us. We would not be able to train neural networks if that was not the case. Okay, very good. So the problem that we are going to tackle today is how to compute gradients. We already know how to compute gradients. We actually showed and went through an example of the analytic gradient that was computed for a simple loss function. So the idea is that you would have, for example, a nonlinear score function like this one, then a per element data loss, an L2 regularization term. Well, the idea of the gradient with respect to the loss is to answer the question, how much is each of these parameters, right, influencing in the loss? Because once you know that, you can update these parameters in the direction contrary to the gradient, so in the direction contrary to the increasing loss, in a way that with these new values, you get a lower loss. In other words, you get closer to the correct model output, to the correct predictions, for example, if you're working with image classification, okay? So that's pretty much the idea. If you can compute the gradients, you can optimize using algorithms like the stochastic gradient descent with all of its cousins, right? So with momentum, with adaptive learning rates, with even Adam. How can we systematically compute these gradients for arbitrarily complex networks? That's the problem. When we're working with a very small and easy to model network, maybe we can do that manually, right? So the first idea would be, of course, to derive the gradient of the loss with respect to all of your parameters. Let's just say, for example, matrix W, and on paper. So to do that manually. For example, if you would have a loss function like this, you could expand this loss function and start doing the partial derivatives. Well, there are some problems with this approach. The first one is that, of course, it's a very tedious and time-consuming approach. So expanding the functions using matrix calculus and lots of manual calculations that are error-prone. You would have to go through this process, and it's just not practical, you know, when you're working with real networks, because they get very big, very fast. It is not a modular approach, so that's a huge problem. If you change the loss, for example, so any element that you would have to change in your network would require the recalculation of all of the gradients, okay, because they are connected, of course. So changing the loss, for example, would require the re-derivation of the loss gradients for the entire model, not just this particular element of the model. So it's not modular. Not feasible for a complex model because it does not scale well. As I said, if you have a fairly complex model, it just becomes impractical for a person to go there and manually calculate the gradients. So we need another way to do that. Instead of doing that, we are going to use a data structure that helps represent and derive the gradients of a model, allowing us to create algorithms that do that systematically. So this data structure that we're going to use are called computational graphs, okay? So computational graphs look like this. They are directed graphs that represent computations performed by a given model. Okay, so it's just a different way to represent our model, a systematic way. And using this way, we can do backpropagation, as we are going to see. Okay, so for a very simple model, for example, if we have this multi-class SVM loss like this in a simple score given by the multiplication of the weight matrix W and your input X. Okay, so these are our nodes. The nodes are going to tell you what each of these operations are. Okay, so we have in blue a node that represents matrix multiplication. We have in red the hinge loss, multi-class SVM loss. We have in green the regularization term. We have in gray this sum here. Okay, so you see that the idea is that we are going to interpret each of these nodes at a time, okay? And again, each node represents an operation. Each operation is going to create a couple of gradients, as we are going to see. Well, when I show you this computational graph, you might think, okay, this is super simple. Why is it necessary, right? So computational graphs might seem trivial for simple networks such as this one, but they are extremely important for representing complex, larger ones. If you were to consider, for example, AlexNet, There are not only the input image, but a lot of different weights, a lot of different activation functions. The loss function comes at the end, and it's problematic to calculate it manually. You know what? Hopefully you cannot hear. I think there's some kind of maintenance going on here, but yeah, let's just power through. So hopefully you can't hear it. I think it's a drill that they're using. Yeah. Anyways. How to use the computational graphs to calculate the gradients of the model. Oh, that's very good. That's very good. I'm happy to hear it. Yeah, so I'm the only one hearing it. That's okay. Okay, how to use the computational graphs to calculate the gradients of the model. So we already know what the computational graphs mean. Now, I just said that they are going to be used to calculate the gradients, right? So what is the technique to do that? During the backward pass of our model, we are going to do backpropagation. So first, let's recap on what the forward and the backward pass represent. For a given network, this is a three-layer neural network, right? We have the forward pass, where the input goes through the whole network. So that's a very easy one. You start, and then you multiply your input by the weight matrix, you sum with the bias, you pass it through the activation function up until the end when you get the score, the predictions of your model. So not a problem here. Today is all about the backward pass. So the forward pass is easy. In the backward pass, the idea is that we are going to consider each part of the model at a time. And at each of these parts, we are going to calculate the gradient. So instead of asking ourselves, what is the gradient, the final global gradient of all of my parameters with respect to the loss, sorry, the other way around, the loss with respect to all of my parameters, I'm going to calculate the gradient locally. So first I start at the end, the loss, and then what is the gradient of the loss with respect to the loss? Very good. What is this, the gradient of the loss with respect to my last node? And then I keep back propagating up until I get to the beginning of my network, which will answer this question. What is the influence of these parameters on my final loss? So it's a beautiful process. Based on the scores and labels, a loss is calculated. So we start with the final loss, which is always a scalar. Okay, so remember that. And the gradients of it with respect to each parameter, weight matrices, bias, and derived using backpropagation in computational graphs. So two important things. First, we need the computational graphs, and then we need to use backpropagation on them to calculate the gradients. Okay, very good. So the strategy today is going to be to work through examples. We are working with two examples of just scalars as inputs, one example of a vector as an input, and a final example with two matrices as inputs, okay? So let's start with the simpler one. Just a simple illustrative loss given by x plus y multiplied by z, okay? So this is the loss, which is going to be our main reference, right? So we start with the loss and then calculate the gradients with respect to it. Sorry, the other way around. The gradient of it with respect to other parameters. So the goal is to calculate the influence of each input, in this case the parameters, on the loss. So let's just put some random values to these inputs. We have x equals -2, y equals 5, and z equals -4. In the forward pass, as I said, it's super simple. We are just applying the operations that each node is implementing. So this node here is a sum. We do -2 plus 5. We have 3. We are going to call the output of this node Q, okay? So Q is given by the sum of the two inputs, x plus y. This is going to be important during the backward pass derivations. And then we have F, which is the final output, in this case, that represents the loss, okay? Which is given by Q times Z. As you can see, Z is one of the inputs, and then it goes straight with the multiplication of one of your intermediate outputs. So F, which is the loss, is given by Q times Z. Not a problem. And then, of course, our loss is -12 here, based on this on these values that we chose. The idea, what we want to find, is the partial derivative of the loss with respect to each of the parameters. Always keep in mind what is the final goal. The final goal is to find the influence of each of the parameters in the final loss so that we can change their values. And as a result, lower the final loss, okay? So in the backward pass, we want to calculate the derivative of the loss with respect to each of the inputs. In order to do that, we'll travel backwards in the computational graph and evaluate the partial derivatives element-wise. More specifically, node-wise, okay? The very first partial derivative that we are going to calculate, as I said, we start on the extreme right, and then we keep making our way up until the beginning of the network, so the extreme left. All right, so the first partial derivative is the partial derivative of the loss with respect to itself. Anything that you change on this function is going to change its value, so the derivative, of course, is going to be 1. Very good, so that's an easy one. The second derivative is, okay, so the idea is you get a node, and then you do the derivatives of this node, and then the derivatives of whoever is connected to this node. So the simpler one is this input here. So what is the derivative of the loss with respect to input z? Well, we know what is the equation for the loss. We just said that the equation for the loss is q times z. So the derivative of q times z with respect to z, of course, is just going to be q. And we know what the value of q is. The value of q is 3. Therefore, the backward propagation is going to be 3 here. The derivative of the loss with respect to this particular input is going to be 3. Another thing that we typically do is that we put the values of this function or of this input on the top of it. So as you can see, -4 here, and on the bottom, the values that you calculated during backpropagation. Okay, very good. So let's keep moving. Now we got to this node here. What is the derivative of this output? Of the loss with respect to this output. So the derivative of f with respect to q. Well, we know again that the function of the loss is q times z. So what is the derivative of q times z with respect to q? Just z. What is the value of z? -4. Very good. So we calculated -4 here. And then things get very interesting. We want to know the derivative of the loss with respect to these two inputs, one at a time, okay? So let's start with y. What is the derivative of the loss with respect to y? How to calculate this derivative if the output value of f is not directly related to y? It is related to y, but in an indirect manner, right? By this equation here. We know that q is given by x plus y, and we know that f is based on the value of q somehow. So they are connected, but not directly. We are going to use the chain rule to do that. So the derivative of the loss with respect to this input y is going to be given by the derivative of q with respect to y, and the derivative of f with respect to q. Very good, that's the chain rule. And there's a bit of a rationale that helps us remember what's going on. If y changes, q is going to change. Of course, you can see the function here. If q changes, we know that f is going to change. To evaluate the changes together, you just have to multiply them, okay? So we are going to be using the chain rule over and over and over throughout the study of backpropagation. In particular, we are going to give names to each of these terms. And these names are extremely important because this is one of the recurrent themes throughout this class. The gradient that is coming into the output of a node. So you do the forward pass, and then during backward pass, there's going to be a gradient coming into the output of a node, right? This gradient is called the upstream gradient. What does the upstream gradient represent? Regardless of how big your network is, it is always going to represent what is the derivative of the loss with respect to the output of your function, okay? So in this case, it's quite easy to visualize what's happening, but we could have 1,000 nodes here on the right. Regardless, the gradient that gets to the output of a certain node always represents how much the output of this node is influencing in the loss, the final loss of your model, okay? That's the upstream gradient. The local gradient represents how much each of the inputs of your node are influencing on its own output, okay? So it's just a local gradient. Very good. And then the downstream gradient is going to be representing how much each of these inputs of the node are influencing in the final output of your model, okay? So this equation that the downstream gradient is always equals to local gradient times upstream gradient is going to hold regardless of your layout. And of course, back to this example here, we know that the derivative of q with respect to y is going to be, so x is like a constant, so it goes to 0, and y is going to go to 1. So we have 1 times minus 4, because of course the derivative of f with respect to q. Z comes out, so we just have minus 4. Therefore, I put it here. So the downstream gradient is going to be minus 4. And then when we look at the other input, x, now we have again the chain rule. And as you can see, the derivative of q with respect to x, y is a constant, it goes away, it's just 1. And then we have 1 times minus 4 once again. So what we got at the end of this example is the influence of each of these parameters in the final loss. We, as you know, use these gradients, these influences, to update the values of these parameters, ultimately making this value of loss go down and down. That's the idea, right? We want the loss to be as small as possible. Very good. So this idea that we have a upstream gradient coming down, we calculate local gradients, and then we propagate downstream gradients is going to be extremely important. As I said, it's going to be a recurrent theme. And the idea here is that it doesn't matter what is happening on the rest of the network. The only thing that matters is what is coming to your local node, okay? So each node does not need to know about the other parts of the graph. The gradients associated with each node are combined to calculate the global derivatives. So the way that backpropagation works is that the nodes are processed independently, but they are connected somehow, and you see how. Let's say that we have a node, it doesn't matter what it's doing, but we have 2 inputs to this node, x and y, and we have 1 output, z. We do the forward pass, we compute the outputs, that's super easy and straightforward, and then we start backpropagating the gradients of the loss, okay? So the upward gradient tells us how much the loss changes if we change the output of this node just a little bit. So as I said, the upstream gradient, the gradient that comes to a node, always tell you how much the loss is being influenced by the output of this particular node. That's very good. And then we have to calculate the local gradients. As I said, the influence of each of the inputs on the output of this particular node. Very good. So the derivative of z with respect to x and the derivative of z with respect to y. What else do we need to do? That multiplication that I was telling you about. Now we want to know what is the influence of x and the influence of y in the final loss of the system. We use the chain rule to do that. So the downstream gradients are always going to be local gradient times upstream gradient, local gradient times upstream gradient. Oh, and by the way, the upstream gradient for a node is always the same, okay? So of course, the downstream gradient is going to be parameter specific, but the specific part of its calculation is just the local gradient, okay? The upstream gradient is, of course, always going to be the same for a certain node. And then one interesting thing happens. When you calculate the downstream gradient, this downstream gradient is going to be connected to another node, right? And it's going to represent the upstream gradient when you are processing this other node. So when you are at other viewpoint. Very good. So by the end of the backpropagation, we'll have calculated the derivatives of the loss with respect to each of the original inputs of the graph. So when you keep going right to left, you eventually will get to the beginning of the network where you have, as a result, the influence of each of the parameters with respect to the loss. Very good. So let's look at another example still with scalar inputs. As you can see, we are calculating the sigmoid function here, and you remember that the sigmoid function is 1/1 plus e to the minus score. And in this case, the score here is the multiplication with the weight matrix, and W2 works as a little bit of a bias, okay? So we have W0, X0, W1 and X1, and also W2. We want to know how much each of these parameters is influencing in the final loss, okay? Very good. So let's put some random values here and calculate the forward pass. So the forward pass is extremely straightforward. We just calculate the outputs by, for example, multiplying these two and then putting these two together, et cetera, et cetera. Very good. So the interesting one is the backward pass. We always start with the base case. We start with the rightmost element. So what is the derivative of the loss with respect to itself? We just discussed that. It's always 1, okay? So we put 1 here. And then we get to the first node. By the way, this class is going to have a lot of examples and a lot of details. So what I try to do is to make it as well annotated, as well commented as possible. So if at any point you get lost, you of course can ask me questions if it's during the class. But if you go to the PDF afterwards, you see that all the slides are thoroughly commented, okay? So I believe that they are self-sufficient. You'll be able to follow all the examples just by looking at the slides as well. And of course, you have the support of the video that is going to be released. Anyways, so we have this node here. The equation that this node is implementing is 1 over x. So what is the upstream gradient? What is coming down the pipe? Well, 1. What is the local gradient? So what is the derivative of the function with respect to the input? So what is the derivative of 1 over x with respect to x? Well, if you remember, it's minus 1 over x squared. I actually put it here, why this is the case. Very good. So now we have the upstream gradient, which is 1, and the local gradient, which is minus 1 over x squared. So now to calculate the downstream gradient, the gradient that is going to keep going through the network, we just have to multiply these two. So we have here minus 1 over x squared times 1. And then, of course, what is the value of x? The value of x here is 1.37 for a final minus 0.53 as the downstream gradient. Okay, very good. As I said, the downstream gradient is going to work as the upstream gradient for the next node. So now we go to the next node, which is just a sum operator. The downstream gradient, the upstream gradient of this node is going to be minus 0.53. So we have the first element. The second one is going to be the local gradient. So what is the derivative of x plus 1 with respect to x? Well, just 1. Very good. So now we multiply the local gradient 1 by the upstream gradient minus 0.53. That's going to be our downstream gradient. Not a problem. So downstream gradient here minus 0.53. Next module. So we are now in a node that we are applying the exponential, the e to the power of x. If you remember, the derivative of e to the power of x with respect to x is e to the power of x, so it doesn't change. Very good. So we have e to the power of x, which is the local gradient, times the upstream gradient. Who's the upstream gradient? Minus 0.53. So this is what we have here. And then, of course, x is going to be minus 1. This is, of course, coming from the forward pass that we already calculated. So as a result, we have approximately minus 0.2. Then we have minus x being implemented by this particular node. We know what the upstream gradient is. We know that the derivative of this node is going to be just minus 1. So minus x derived with respect to x is just minus 1. Therefore, our downstream gradient is going to be the multiplication of these two, 0.2. Very good. Finally, we got to a node where we have two inputs. So as you know, when we have two inputs, we are going to have two downstream gradients. The upstream gradients, the upstream gradient for both of them is going to be the same, so 0.2. What is the local gradient? We have two local gradients now, right? So we have these two inputs, say x and y. The derivative of them with respect to x is just going to be 1. And with respect to y is also just going to be 1. So something interesting is happening. Now we are multiplying the upstream gradient by just 1. So as a result, in practice, we are just propagating the value of the upstream gradient to the downstream gradients. So this is an interesting behavior for the adding node, okay? So we have an add node, we just got the upstream gradient, and we copy this upstream gradient to the downstream gradient of its two inputs. Very good. So now we get to another node that is implementing the addition, right? So what do? We don't do any calculation anymore because we already know what is the behavior. We just propagate the 0.2 to both of the downstream gradients. So 0.2 comes to this downstream gradient. It also comes to this other downstream gradient. That's perfect. Now we are in a multiply node. So let's see what happens. The function that is being implemented by this node is x times y, of course, being two different inputs. The derivative of them with respect to x is just going to be y. The derivative of them with respect to y is just going to be x. So that's interesting. It means that we are multiplying to find the downstream gradients, the upstream gradient, as always, and the other input. So if we are calculating the downstream gradient for y, for example, we are multiplying the upstream gradient by x, and the other way around as well. So what we need to do here is to get the upstream gradient and multiply by the other input when looking at a certain downstream gradient. Let's look at W0, for example. So for W0, the downstream gradient is going to be the other input, which is -1, multiplied by the upstream gradient. So -1 times 0.2, which is which is minus 0.2 as well. It's here. And then for x0, we do the exact same thing. We get the other input, which here is 2, multiplied by the upstream gradient, 0.2. So we have approximately 0.4. The reason why it's not 0.4 is because I did an approximation here, and therefore it propagated a little bit, but you can consider that it's 0.4. So we found the behavior of another node, and these are extremely helpful because when you know the behavior of a certain node, you not only can implement it in code easier, you can also calculate it manually way faster. So when we get to this other node, we already know exactly what to do, right? If we are in this particular parameter, W1, what is going to be its downstream gradient? We already discussed that. It's going to be the upstream gradient, 0.2, times the value of the other input. So 0.2 times -2, so minus 0.4. And for this one, it is going to be the other input, -3, times the upstream gradient of 0.2, so minus 0.6. And there we go. You now have the gradient of the loss with respect to each of the inputs. So that would be actually the derivative, right? So the derivative of the loss with respect to each of the inputs, if you put them all together, this is your gradient. Very, very good. We created this computational graph using the most basic nodes, primitive functions possible. One can use more complex nodes to simplify the computations if you want. So if you note, these 4 nodes here are implementing the sigmoid function, but you could represent the sigmoid function itself as being a single node, okay? So let's see here how the sigmoid function looks like. All right, so we know that the sigmoid function looks like this, and the derivative of the sigmoid function with respect to its input, in other words, the local gradient of the sigmoid function, it turns out it's given by 1 minus its output multiplied by its output, okay? So let's do this calculation again, now considering the sigmoid function as a single node. So if the sigmoid function is a single node, we just have to calculate its local gradient, which we already know the formula for, multiply it by the upstream gradient, and there's it. This is it. So what is the local gradient? 1 minus the output. What is the output here? 0.73. So 1 minus 0.73 times the output itself, 0.73, times the upstream gradient, which in this case is just 1. So 0.2 is going to be our downstream gradient. And look how interesting. This is exactly what we calculated when considering each node at a time. We put a bunch of nodes together. They represent the sigmoid function. This is exactly the same thing as calculating the upstream gradient, local gradient, and then downstream gradient for each of these nodes. That's very good. Another thing that you can note is that some patterns are being formed in this gradient flow. So when I was talking about, for example, the sum node, I told you, look, you just have to get the upstream gradient and propagate it to the downstream gradients. So this is a pattern. I said that for the multiplication node, what you were doing was multiplying the upstream gradient by the other input that you were considering. Very good. So these are the patterns that we are talking about. And of course, they make calculations easier. They can be easily programmed using the language as well. Let's look at a couple of them, 4 of them. You can consider that they are like electronic gates. The sum would be like an AND gate where you are just distributing the gradient. So your downstream gradient is 2 here, and the upstream gradient is 2. And as you can see, the downstream gradients are also going to be 2 and 2. Very good. Let's look at the copy gate now. So the copy gate is just going to get a particular input and copy it to both the outputs. You might ask yourself, when would I use such a gate? If you're talking about, for example, the calculation of the loss, and the calculation of the loss is formed by both the data loss and the regularization term. Well, the weight matrix is used in both of them. So at some point in your computational graph, you will need to save the values of the weight and to send them to 2 different places at the same time. That is when a copy gate might be useful in a computational graph. And the idea is, well, my weight matrix was now propagated to 2 different places. Let's see how much it influenced in the loss at each of these parts of this bifurcation. So I go back and put them together. That's the idea. You get the upwards gradient for these 2 different legs of your function and put them together. So the upstream gradient of one of them was 4, the other one was 2. You put the 2 of them together, 6 as the downstream gradient now. Very interesting behavior. Then you have the multiply gate. As we said in the multiply gate, let's look at this input, for example. What is going to be the downstream gradient for this input? Well, the value of the other input, in this case 3, times the upstream gradient 5, 15. What about the other one? Well, it is going to be the value of the other input, in this case 2, times the same upstream gradient of 5 for a final value of 10. Then we have the max gate. So this is an interesting one because it's a nonlinear gate, right? For the input that is maximum, in this example 5, the local gradient is going to be 1. If the local gradient is 1, the downstream gradient is going to be 1 times the upstream gradient, of course. In this illustration here, the upstream gradient was 9. Therefore, the downstream gradient is going to be 1 times 9, therefore 9. The local gradient of the non-maximum input is going to be 0. Why? Because you see, if you change this input 4 here just a little bit, the output that is being generated by this input is not going to change at all. So the output will remain in 5. So these variations, these little variations in 4, are not influencing in the output. Granted, if 4 becomes higher than 5, then this is a problem, right? So if you change it a lot, the behavior is going to change. But for the gradient, just changing it a little bit is not going to change the output at all. Therefore, the local gradient for this input is 0. 0 multiplied by the upstream gradient is still going to be 0. In other words, the summary, right, the simplified behavior of this node is going to be: you get the highest input, and then you just put the upstream gradient on the bottom of it. Very nice. Well, so far we've been talking about backpropagation with scalars as parameters. What about vector valued functions? Okay. By the way, I already discussed a lot of things and I didn't ask for any questions. So do you have any questions? And is it overall clear what's going on to this point? All right, so I'll just keep going then, and if you have any questions, of course, you can ask them at any time. Very good. So before we move on into an example where we have vectors as inputs, let's do a quick recap on the different types of derivations that we are going to work with. The simplest one is just considering that the 2 parameters involved are scalars. So let's say that we are calculating the derivative of y, and y is a scalar with respect to x, and x is also a scalar. So these examples that we were working with. Well, we know that the dimensions of the output are also going to be 1, so it's also going to be a scalar. It reflects local linear approximation. It answers the question, if we change the input a little bit, how will it affect the output? Very good. So now what happens if our input is not a scalar anymore? Let's say that the output is a vector, a column vector, for example. The derivative now is called a gradient. And the gradient is nothing else than the composition of the partial derivatives of your output with respect to each of the elements of the input. Okay, so it's actually very simple. We have an illustration of it here. Let's say that your input x had 3 elements. The partial derivative of y, which is a scalar, with respect to x, which has 3 elements, is going to have the derivative of your output, the derivative of y, with respect to each of the elements of x. So the derivative of y with respect to x1, with respect to x2, and with respect to x3. So there is an extremely important pattern going on here. The dimensions of the output are going to be given, in this particular case, by the denominator, okay? So the numerator has got just 1 dimension, and the denominator has 3. So the dimensions of my output are going to be 3 by 1, okay? So always remember that when you're calculating the derivatives, your output is going to have the dimensions of the denominator times the dimensions of the numerator. This is going to be very helpful for some other examples, okay? So in this case, we are doing the derivative of a scalar with respect to a vector. What is the output? What are the dimensions of the output? Definitely the same dimensions of this vector. Is that the case? Yes, it is. You can see here in the illustration, we started with a scalar, the derivative with respect to a vector of 3 dimensions. Our output is by itself a vector of 3 dimensions, okay? Very good. So now we go a bit more general. We go to different dimensions for x and y, and of course they are higher than 1 in this case. So we have x with n dimensions and y with m dimensions. Without even thinking about it, what did I just say, right? That the output is going to be given by the dimensions of the denominator times the dimensions of the numerator. So the dimensions of the denominator here were n, so n by the dimensions of the numerator, which were n, so n by n. Very good. So let's look at an illustration on how that would work. Let's say that we have a x parameter, an x input with 3 dimensions, and a y output with 2 dimensions. What is the derivative of y with respect to x? First, we know that in terms of the number of dimensions, we have 3 times 2. So we have here 3 by 2 dimensions. So our matrix is going to have, regardless of the values, 3 rows and 2 columns. So you can look at the formula, so this formula here, or you can use the rationale, which I think it's easier to remember down the line, right? The idea here is exactly the same that we did for the gradient. The idea is that for each element of the output, we want to know what was the influence of each element of the input, okay? So in the first element here, when y and j are 1, what are we asking? We are asking what is the influence in the first element of the output, y1, created by the first element of the input, x1. So in this element here, we have when I equals 1 and j equals 1, the influence on y1 by x1. But this time, instead of a gradient, because if that was just a gradient, we would calculate the same influence for x2 and x3. That's very good. But now our output has got 2 elements. So what is the influence of x1 in the other element of the output? So what is the influence of x1 in y2 now? And then you keep going and you find what is the influence on each element of the output based on each element of the input, okay? So this matrix is called a Jacobian matrix, okay? When you are dealing with a scalar and a vector, this is called the gradient. When you are dealing with inputs, when you are dealing with both x and y in different dimensions, this is called a Jacobian. You can think of a Jacobian as a matrix where each column is a gradient itself, okay? So let's say this column here. All the elements of this column are talking about the influence of x in the first element of the output, correct? So the influence of x1 in y1, of x2 in y1, and of x2, sorry, that should be x3. Yeah, so I'll correct this one. So of x3 in y1 as well. So this is a gradient, this is also a gradient, okay? Very good. So now let's look at the dimensions with respect to inputs that are not scalar anymore. We are, again, working with a single node. We don't care about what's happening in the rest of the model. We just care about the node. So what's coming into the node, the upwards gradient, what's going on inside of the node, the local gradients, and what's going on back propagating throughout the node, which are going to be the downstream gradients. Well, let's consider that x has got dz dimensions, sorry, dx dimensions, y is going to have dy dimensions, and z is going to have dz dimensions. A quick question for you. The loss is always going to be a scalar, okay? So the final loss, L, is always going to be a scalar. Given that the loss is a scalar, what are going to be the dimensions of the upstream gradient? In other words, we are calculating the loss, the gradient of a scalar with respect to a vector of dz dimensions. What are going to be the dimensions of this gradient? So let me give you a couple of seconds here. Okay, so this is always going to happen, okay? The upstream gradient is going to be the loss, the final loss of your system, which is a scalar, with respect to the output of your node. The output of my node here has dz dimensions. So I know for a fact that my upstream gradient is also going to have dz dimensions, okay? Very good. What about the local gradients? Well, now the local gradients are considering a, okay, so let me go back here to illustrate. In my local gradients, this y here now has dz dimensions, and this x might have dx dimensions or dy dimensions, okay? So now we know that the local gradients are going to represent Jacobian matrices. Okay, so I have it here, what a Jacobian matrix looks like. And if you remember, the dimensions of the Jacobian matrix are going to be given by the dimensions of the denominator by the dimensions of the numerator, okay? So it's very hard to get lost there. The dimensions of the denominator here are dx, and the dimensions of the numerator are dz. Therefore, the dimensions of the output are going to be dx by dz. Same thing for the other local gradient, the local gradient with respect to y. The dimensions are going to be dy by dz. Very good. So now we know what are the dimensions of the upstream gradient. We know the dimensions of the local Jacobian matrices. We can calculate the downstream gradients as well. By the way, when you're looking at local gradients, now you are calculating the gradient of the loss, which again is a scalar, with respect to a vector. What are the dimensions of this vector? Dx. So regardless of the dimensions of the local gradients and the dimensions of the upstream gradient, I know for a fact that the dimensions of this downstream gradient are going to be dx, and for this other one, dy, necessarily, okay? So remembering these little rules for dimension is extremely useful, because you will always remember that when you're doing the derivative of a scalar with respect to a vector, the final dimensions are those from the vector. If you are doing the derivatives of something with crazy dimensions here and crazy dimensions here as well, your output is always going to be the dimensions of this one times the dimension of this other one, okay? So it's kind of easy to remember, I believe. But let's look at an example using ReLU to illustrate, okay? So now we have a single input, but this input is a vector. So it has got 4 different elements. We then apply ReLU, which, if you remember, is the max between 0 and the value of the input. In other words, if it's a positive value, you just pass it through. If it's a negative value, you change it by 0. So the forward pass is extremely simple, of course. The forward pass here is going to be 1 in this position. This is a negative value, it goes to 0. This is a positive value, goes to 3. So it doesn't change. And it's a negative value here, again, 0. Very good. So we do the forward pass, we calculate everything, we calculate the loss at the end of the computational graph, and then we start coming backwards. It doesn't matter for how long we're coming backwards. What is important here is that at some point in the calculation of the backpropagation, we got an upstream gradient. What was the upstream gradient? Well, it was like this. Let's first think about the dimensions, right? So the dimensions of the upstream gradient, as I said, are going to be given by the partial derivative of a scalar, which is the final loss of your system, with respect to your output. What were the dimensions of my output? 4 elements here. So I know for a fact that the upstream gradient is also going to have 4 elements, which is what we got here. So the upstream gradient, regardless of how we calculated it, is going to be 4, minus 1, 5, and 9. So now we go to the calculations of the local gradient. Well, the local gradient is going to be the derivative of y, your output, with respect to the input, x. We already know that this is going to be a Jacobian because we have 4 elements here in y and 4 elements in x. What are the dimensions? Well, once again, the dimensions of the denominator, 4, by the dimensions of the numerator, 4. Very good. So the dimensions are 4 by 4. Our matrix is actually going to look like this. It shouldn't be scary at all. As I said, each column is a gradient. So let's take the first column, for example. The first column is going to tell you what is the influence of each of the elements of your input, x1, x2, x3, x4, with respect to one of the elements of the output, with respect to y1, 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 y1. Each of the columns are going to tell you that. So each of the columns represent a gradient by themselves, okay? That's very good. So now let's look at the particular behavior for the ReLU function. In ReLU, the first output, so this output here, is only influenced by the first input. So it doesn't matter what happens with these 3 inputs in terms of this first output. The only thing that matters are the changes in this particular element here. In other words, the partial derivative of this output with respect to this input and this other input, and yet this other input here, are all 0. The partial derivative of y1 with respect to x2, x3, and x4 are all 0, okay? So this is what we had for the first column of the Jacobian matrix. And this reasoning is going to be the same for the second, the third, and the fourth column, okay? So this is how our Jacobian matrix looks like. As you can see, only the elements on the main diagonal are non-zero, potentially non-zero, actually. Now, another analysis, right? So what are the values of each of the outputs with respect to each of the inputs? Well, the gradient of positive valued inputs is going to be 1. In other words, let's say that we are working with 3 here. If you change 3 just a little bit, if you change 3 to 3.1 or maybe 2.9, the output is going to change with the same ratio, okay? So the gradient, of course, is going to be 1. For the negative values, if you change them just a little bit, given that they don't become positive, the output is not going to change at all. The output is going to stay as 0. In other words, changes in the input are not influencing in the output. So for this element and this element here, the local gradient is 0. So that's why we have 0 here and 0 here. And for the positive valued ones, the gradient is 1. Very good. So now we calculated the local gradient, which is a Jacobian matrix. So the Jacobian matrix looks like this. What do we need to do to calculate now the downstream gradient? As you know, you just have to multiply the local gradient by the upstream gradient. Very good. So you do this multiplication out, of course, 4 times 1, and then 0 times minus 1, 0 times 5, 0 times 9, and you keep, excuse me, you keep moving on. As you can see in the output, so in the downstream gradient, we have the value of the upstream gradient whenever this input was positive, and we have 0 whenever the input was negative, okay? So that's a very interesting behavior as well. As you can see, the Jacobian, meaning the local gradient, was very sparse. The off-diagonal entries are all 0. So all of these guys are 0, and these guys as well. So in other words, we are never going to explicitly form the Jacobian. And the reason why is because it can get extremely big, extremely fast. In the next example, I'll show you that for a relatively small input, you can explode the memory of your computer if you are trying to calculate the Jacobian element-wise. So calculating everything in the Jacobian, okay? So instead of doing that, what we need to do is to look at the behavior of each of these nodes and see what are the outputs of the Jacobian without actually having to calculate it, okay? So we are going to implicitly find a multiplication that is going to give us the results of the Jacobian. This analysis, this strategy, right, of not calculating the Jacobian, but rather looking at another way to get its value, holds for a lot of the functions that we use in deep learning. In the next example, I'll show you this analysis for the multiplication gate, okay? It is paramount in backpropagation to calculate these Jacobian matrices in an efficient way, because as I said, otherwise it is just not going to be practical. They can get very big, very fast. For ReLU, this behavior is actually very trivial, okay? So what happens is that you look at the element of the upstream gradient. If this element is positive, then you just pass it through. If it's negative, you just pass 0, okay? And then what we did here is that we reduced 16 operations of the Jacobian down to just 4 simple comparisons, okay? This form is going to be particular for ReLU. In other words, when you are working with the multiply gate, this is going to be different. If you're working with different gates, this behavior is going to be particular to these gates, okay? So this formula here only holds for ReLU. Very good. So we started with scalar parameters, then we moved on to vector parameters, and now we are going to talk about matrices as parameters. Our inputs are going to be matrices, the output of our nodes are going to be matrices as well. So it can get a little confusing, but let's go step by step. The dimensions of the first input are going to be now dx by mx. It is a matrix. The dimension of the second input are going to be dy and my. The dimensions of the output of our node are going to be dz, mz, okay? The loss L, regardless of how crazy your computational graph might be, is always going to be a loss. It's always going to be, it's always going to be a scalar, always going to be a single number, okay? So when you do the forward pass, you're calculating the outputs. When you're doing the backward pass in this upstream gradient here, we know exactly what its dimensions are going to be. They're going to be the dimensions of the output itself. So the dimensions of this upstream gradient are going to be dz, mz. Why? Because we are doing the partial derivative of the loss with respect to a matrix. So we get the dimensions of this matrix here. They're going to be the dimensions of the output. Very good. When we look at the local gradients, we know that they are Jacobians now, but what about the dimensions? Well, you follow the same rules that I was talking about. So what is the derivative of z with respect to x? We know that the dimensions of x are dx mx, and the dimensions of z are dz mz. What are the dimensions of the local gradient then? Well, the dimensions of the denominator, dx mx, by the dimensions of the numerator, dz mz. Very good. We do the same thing for the other input as well. So in this other input, the dimensions of the denominator, dy my, by the dimensions of the numerator, dz mz. So we know what the local gradients are going to look like. By the way, another way to remember that, right? Because it's strange to see the dimensions of a matrix being a matrix by a matrix, right? But if you do it on paper, you see that For example, if this one here was a 2x3 and the output was a 2x2, in the end, you would have a 2x3 matrix where each element is by itself a 2x2 matrix, okay? So when you do it, as I said, on paper, at least once, you see that it's not that confusing. And as long as you remember that when you're doing the derivative, you are going to have the derivative of the dimensions of the denominator by the dimensions of the numerator, you will definitely be fine. Now, when we go to the downstream gradients, again, always remember what we're trying to do. In the downstream gradients, we are doing the derivative of a scalar with respect to a matrix. So we know that the output is going to have the same dimensions as those of the matrix, right? So the dimensions of this downstream gradient are always going to be dx mx, and of this one, dy my, okay? Very good. So yeah, the reason why I keep looking at the clock is because I think this example is going to take a bit more time. But okay, so let's start this example, and hopefully we'll be able to get to the end of it. If not, in the beginning of next class, we'll restart from here. Okay, very good. So now we have two matrices as inputs. Okay, so our parameters are 2x3 and this one 3x4. Okay, these are the dimensions. The dimensions of the output, because we are implementing now a matrix multiply, are going to be n by n. Okay, so of course you know that in order to multiply two matrices, this dimension has got to be the same as this one, and the output is going to get the first and the last dimension. So n by n, this is what our output says here. Okay, very good. So we calculated the forward pass, we calculated the output at the end. Based on the output and the labels, we calculated the loss, and then we started backpropagating. At some point in this process, we got the following upstream gradient. By the way, dimensions of the upstream gradient. Well, the dimensions of the upstream gradient are going to be exactly the same as the dimensions of the output. So the dimensions of the output, n by n, the dimensions of the upstream gradient, as expected, n by n as well. Very good. So now let's focus on the calculation of the downstream gradient for the input x. Okay, so we want to calculate the downstream gradient of this particular parameter here, which is going to be the derivative of the loss with respect to x. Without doing any calculation, without thinking about it long enough, we can already tell what are the dimensions of this downstream gradient, because this downstream gradient is the derivative of a scalar with respect to a parameter, which is n by d. Therefore, its dimensions are also going to be n by d. That's very good. So we already know the form of this downstream gradient. So I was telling you that we should not just go ahead and calculate the Jacobians, right? Because they can be extremely big. For example, if you look at the Jacobian dy dx, so the local gradient of y, right? So the local gradient of dy dx is going to be given by n times d, which are the dimensions of the denominator, by the dimensions of the numerator, n by n. Very good. For a neural network, we might have, for example, n equals 64. Okay, so if we are working with a mini batch of 64 images at a time, for example, this n here would be easily 64, sometimes way more than that, by d, which represents the number of dimensions of x. So let's say, for example, that we are working with 128 by 128 images, just considering a single grayscale channel. Actually, I think this number is for, yeah, it's for 64, yeah. Consider images of just one channel and 64 by 64 pixels. If you were to flatten this image, stretch it out, that would be 4,096 dimensions. So we would have a matrix as an input, a full mini batch of 64 by 4,096. Each column would represent an image, and you have 64 rows because you have 64 images being presented to the system at a time, to the model at a time, okay? Very good. So the Jacobian, as I said, would be n by d by n by n. If you calculate that, right? So if you multiply 64 by 4096 and then multiply 64 again by 4096, you would have to use a lot of space just to represent these numbers, let alone calculate them, because there's a certain processing that has got to be done for the calculation of each of these elements, right? But just forget about that. Let's say that you already calculated these elements and you just wanted to save them, for example. Considering floating points of 32, for example, meaning 32 bits per number, the Jacobians would take 256 gigabytes for this one, which is the smallest one, and 16 terabytes for the other Jacobian, okay, for the other local matrix. Again, I'm not talking about processing. I'm just talking about how to store these gigantic matrices. This goes without saying is not something that we can work with. This is not a super complex network. So the number of elements that you pass through the network, the number of mini batch samples is typically higher than 64. Not typically, but sometimes higher than 64. But the number of dimensions is typically higher than 4096. So this is super problematic, right? We want to calculate these gradients, but we cannot calculate the Jacobian matrix explicitly. We cannot go through each of these elements and calculate them. We can't save them, let alone calculate them, okay? So we must work with them somehow implicitly. We need to do the same thing that we've done for the last example. We need to know how these Jacobian matrices work, because they are typically very sparse. Okay, so let's start with the local gradient of x, okay? So how much is the output of this node being influenced by this parameter x? So the derivative of y with respect to x. Again, dimensions, well, the dimensions of x and d by the dimensions of y and n. Okay, very good. So this is going to be a matrix of 2 by 3, where each element itself is a matrix of 2 by 4. So this is how it's going to look like. In other words, we have, so this is just a simplified way to represent the output, you know? So we have the derivative of your output with respect to the first element of x, this element here, the derivative of the output with respect to first line, second column, so this element here of x, and so forth. As I said, a 2 by 3 matrix, and each of these elements is a matrix itself. Of how much? Of 2 rows and 4 columns. So we are going to concentrate in just a slice of the local gradient, just this first one, which, as I said, by itself is a matrix, okay? Let's take a closer look then at the first element, the derivative of the output with respect to the first element of parameter x, x11. So we are going to refer to this as just a local gradient slice. The derivative of y11 element, of the y11 element, with respect to x11 is going to be given by this particular number here. So again, we are zooming in the local gradient, right? We started like this. This is actually a matrix, and this matrix is going to have the dimensions of the output, n by n, okay? The first element of this matrix is the derivative of this particular element of the output with respect to this particular element of the input. That's very good. We're getting to some, we're getting to a point where things actually make sense, right? So now we need the equation of this element here so that we can calculate its derivative with respect to x11. So this element here, remember, we are doing matrix multiply. So this element here, y11, is actually the multiplication of this first row of x and this first column of w, okay? So x11 times w11, x12 here by w21 here, and then x13 by w31. Very good. So this is the equation for the first element of the output, which is this one. what is the derivative of this first element of the output with respect to x11? Well, we have x11 here. So after the derivative, we're going to be left with w11. There's no x11 here. So this is going to go to 0, and this is going to go to 0 as well. So the derivative is just w11. Okay, very good. So let's keep going. That's very nice. In the second one, what is the equation for the second element of the output? Well, the equation for the second element is going to be the first row of x again, but now by now times the second column of w. So we have x11 w12, x12 w22, and x13 w32. When you do the derivative of this with respect to x11, you are only left with w12. Okay, very nice. So you started probably noticing the pattern that we're following. As you can see, we are just grabbing the values of the first row of your matrix W, right? So we have 3, we have 2, 1, and -1 as well. So if you were to calculate it manually, you would see that the other two values are in fact 1 and -1. So this is the first row of this slice of the local gradient is simply a copy of the first row of W. Now let's go to the second row. Well, in the second row, if we were to go through the same rationale, find the equation of the output element, and then derive this element with respect to x11. Well, the equation of this first element of the second row of the output is given by x21, w11, x22, w21, and x23, w31. As you can see, we don't have x11 here. So x11 is not influencing at all this element in the output. Therefore, this derivative here is going to be 0, of course. And you see that all the other derivatives are also going to be 0. Why? Because x11, this value here, is not influencing in all of these outputs at all. That's very good. So now going back, so zooming out a little bit again, we have that the local gradient with respect to x is given by a 2×3 matrix, and that each element of this matrix is a matrix by itself. We just calculated first such matrix, okay? So we now have the first element of one of the local gradients, dy dx, sorry. Thus, we can calculate the first element of one of the downstream gradients. So now that we have this element here, we can also calculate the first element of the downstream gradient, this one here, okay? And the reason why we're going element by element is because it's super tedious to do to all of them, but if we understand what happens with one element, you see that calculating all the others is way easier, okay? So again, the formula of the downstream gradient is going to be the local gradient times the upstream gradient. Very good. We were just working with the local gradient here, and instead of calculating the whole local gradient, which, as I said, is a gigantic matrix, we are just going to look at the first slice of it, at just this part here. This one we calculated manually, right? So instead of looking at the whole thing, we are going to look at the multiplication, right, of the first slice of the local gradient with respect to the upstream gradient. So this multiplication is going to be an interesting one. We are multiplying this matrix here by this upstream gradient, and as a result, we are getting a scalar. We know that this multiplication is going to give us just a single element in the downstream gradient. So a matrix multiplied by another matrix, and as a result, we have a scalar. So this is actually not a matrix multiply. This is an inner product between these two matrices. When that happens, we are actually calculating what is called the Frobenius inner product, okay? So as I said, this is not a matrix multiplication. We are just calculating the value of a single output element in the downstream gradient. Therefore, we are calculating the Frobenius inner product. These are the two matrices that we are working with. Again, this is the first slice of the local gradient, and this is the upstream gradient. And then you do an element-wise multiplication, 3 times 2, 6, plus 2 times 3, 6, etc., etc. So if you do this calculation, this is going to sum up to 0, okay? So this first element is going to be 0. Something very interesting happened here. As you can see, the actual calculations that we did to find this one element of the downstream gradient were 3 times 2, 2 times 3, 1 times minus 3, and minus 1 times 9. That means that we are actually using the values of the first row of W and multiplying them by the values of the first row of our upstream gradient. So that's super interesting, right? There's nothing new that was coming from the local gradient. We calculated the local gradient, of course, but in the end, to calculate the downstream gradient, we only had to look at the values of the first row of W and the first row of the upstream gradient. So you can start seeing what is the form of this implicit calculation. Again, we want to skip the calculation of the Jacobian altogether. And this looks like a possibility now, right? If we were to look at the last element here, so doing the exact same thing we did for the first element, let's say that we were to do that for the last element, well, the local gradient slice would look like this. And then this local gradient slice multiplied by the upstream gradient would give us the last element of the downstream gradient, okay? And if we were to calculate it again, we would see that we were multiply the second row now of the upstream gradient by the third row of W. Again, a row of W by some row of the upstream gradient. So that's extremely interesting, right? Using the same reasoning, we calculate another slice and note that, yet again, the element of the downstream gradient is given by the inner product of one of the rows of the upstream gradient, in this case, the second row here, and a row of the weight matrix, in this case, the third row here. This is super, super interesting. This behavior is generalized using this expression here. Note that we do not need to calculate any slice at all. In other words, we do not need to calculate the Jacobian at all. Because if you calculate the Jacobian, you see that the only thing necessary is to multiply one of the inputs by your upstream gradient. So that's a great and beautiful realization, right? And that makes sense with the behavior that we were discussing for the multiply gate. Do you remember how it was the behavior of the multiply gate? We would, given 2 inputs in an upstream gradient, we would multiply to find the downstream gradients of one of them, the value of the other input by the value of the upstream gradient. We are doing something similar here. We are, in order to find the downstream gradient for X, multiplying some values of W by some values of the upstream gradient. That's extremely interesting. A heuristic, right, to remember exactly what to do is that this is the only way that the shapes are going to work out. So in order to find, this is the final formula, right? In order to find the downstream gradient of X, you just have to multiply the upstream gradient by the transpose of your weight matrix W. And by the way, in order to calculate the downstream gradient of W, you are going to do a similar thing. You are going to multiply the transpose of X by the upstream gradient. Again, that's the only way that the shapes are going to work out. So this is an easy way to remember. This particular behavior, similarly to what we had with ReLU, is going to be exclusive for the multiplication gate, okay? So if you are working with other gates, what gates did we look at? We looked at the max gate, we looked at the multiply gate, but if you were working with the copy gate or with the sum gate, actually the sum gate is super easy. As you remember, you just have to copy the upstream gradient in the downstream gradients. But my point is, any particular gate, any particular node is going to have a particular behavior that is going to avoid the calculation of the Jacobian, okay? If we were required to always calculate the Jacobian, backpropagation would just not work at all. But hopefully this is not the case. I mean, fortunately, this is not the case. All right, so how are we doing in time? Very good, yes, 11:20, that's perfect. So as a quick summary, we are first going to represent our model using computational graphs. These computational graphs are going to have a bunch of nodes. Each node is going to represent a particular operation. It can be a multiplication, a sum, a max, etc. In the forward pass, we are going to compute the outputs of our system. Based on the outputs, we can compute the loss, and then we start backpropagating this loss. We are going to, in the backward pass, use backpropagation to calculate the gradients around each node individually, right? In a way that it's easy, for example, to implement in code. And then we keep backpropagating up until we get to the gradients in the beginning of the network, which are our final objective. During the backward pass, each node in the graph receives an upstream gradient and multiplies them by the local gradients in order to compute the downstream gradients. That's perfect. So once we have these downstream gradients, we can keep propagating these gradients down the network up until the beginning of it. And just keep in mind, when you get to the beginning of it, the piece of information that you have, this extremely valuable piece of information, is how much each of these parameters influenced in the final loss, which is also a scalar, by the way. And then based on this, we can use the optimization algorithms. We can use stochastic gradient descent, we can use atom, etc., to change the value of these parameters and ultimately change this loss as well. Well, the very last thing, this is going to be sort of a cliffhanger for the next class. So far, our classifiers don't respect the spatial structure of the image. So since the second part of the course, we've been saying that, you know, just get an image, flatten it out, and then put it as an input to the neural network. We know that we can use handcrafted features such as SIFT, the histogram-oriented gradients, etc., to represent this image in a different way. Now we are going to use a type of neural network called convolutional neural network to systematically find this representation of your original image. And this representation, of course, is going to be found and then used as the input of neural networks, okay? So this beautiful composition of what I just explained is known as convolutional neural networks. So we are finally going to talk about CNNs in the next class. And by the way, a final announcement. Since your fourth assignment works with CNNs, I'm asking you to implement simple CNNs using PyTorch. I'm only going to release it on Thursday. And since this is the case, I think that, I think it's okay to do that. We can extend the deadline of assignment 3 to Thursday, okay? So on Thursday, we are going to discuss convolutional neural networks. I'm going to release assignment 4, and I'm also going to have the deadline for assignment 3. So you have a couple of extra days, okay? Sounds good? All right, thank you so much for bearing with me until the end of this class. And I'll see you all Thursday, if you don't have any questions, of course. Okay, thank you.